Our theme is prototypes, demonstrating technology, promises, and pitfalls. A research aircraft is a designed-for-purpose airplane to go get specific technical knowledge that is then applied in the design of other aircraft. It might be structures, it might be aerothermal, aerodynamics, propulsion, made-for-purpose airplane. A prototype is a pattern, the beginnings of an aircraft that we produced in quantity and turned over to the average pilot. The distinguishing mark between a research vehicle and a prototype is that they answer a specific operational need. And prototypes have been with us since the beginning of flight. Initially, they were probably more based on imagination of what flight should be than sound aerodynamic principles. But as those principles became known and understood, we began to answer specific operational needs, operational questions, such things as how do we lift extremely heavy loads? And are there alternate forms of propulsion that can take us higher and faster? And the holy grail of aviation, how do we marry the vertical flight of a helicopter with the speeds of a fixed-wing aircraft? This is probably the most prototyped and most explored concept in our aviation history. How do we take short-range fighters and escort long-range bombers? And how do we work over vast expanses of ocean without an airfield and repair facilities available to us? Well, these and the 7 you're going to hear today have certain common traits to them. The engineers and the pilots knew they were going to operate in an oxygen-nitrogen atmosphere, be subjected to 32.2 feet per second squared pull of gravity. The pilots knew very well their airfield and the surrounding terrain, and they knew they had to make a successful takeoff and landing on that first flight. All of them share this characteristic except one. And suppose you had to build a prototype here on Earth that would not fly in an oxygen-nitrogen atmosphere, would be subjected to only 1/6 the pull of gravity. Your airfield had never been seen or visited by a human being. And to be successful, you had to make a landing followed by a takeoff. Neil A. Armstrong flew 78 combat missions as a naval aviator from the aircraft carrier Essex during the Korean War, and he subsequently served 17 years with NACA and later NASA as an engineer, test pilot, astronaut, and administrator. As a research pilot at NASA's Flight Research Center at Edwards, he flew most of the early supersonic jets, including the X-1, the variable swept wing X-5, the vertical takeoff and landing X-14, and the well-known X-15, which he flew to over 200,000 feet altitude in Mach 5.74. He transferred to astronaut status in '62 and commanded Gemini 8 in '66 when he performed the first successful docking of 2 vehicles in space. And as spacecraft commander for Apollo 11, he, with colleagues Mike Collins and Buzz Aldrin, completed the first landing mission to the moon. He's been the holder of 13 world records in aviation and space. He received his engineering degrees from Purdue University and University in Southern California. And between '71 and '79, he was professor of aerospace engineering at the University of Cincinnati. He's a member of the National Academy of Engineering and is a fellow and a charter member of this society. So it's my great pleasure to introduce Neil Armstrong to tell us about the Lunar Lander research vehicles and the Lunar Lander training vehicles. Neil?
Thank you very much. Thank you, Paul. Good morning to all of you. The very first SETP Symposium was held precisely 1/2 century minus 1 week ago. On that Saturday, the last day of the conference and the day of the first annual SETP banquet, the Soviets launched Sputnik. Americans were thunderstruck. Almost immediately here in the U.S., there were serious talks about going to the moon. In the military, in the National Advisory Committee for Aeronautics, NACA, and in various industry advanced project groups. As a result of testimony that had been given by a variety of experts, Congress was expressing substantial interest. Even before John Kennedy was elected, the House Committee on Science and Astronautics, in their 1960 report, recommended that, quote, a high priority program should be undertaken to place a manned expedition on the moon in this decade, end quote. NASA's 10-year plan at the time was to target a lunar landing after 1970, although their own studies indicated it could be done earlier. Soon after President Kennedy's call to go to the moon in 1961, a number of researchers in government and in industry began to think about the various aspects of a lunar flight. Among them were a few engineers at NASA's Flight Research Center, FRC, now Dryden at Edwards. Those of us there at the time, like most of the industry, envisaged a multi-stage spacecraft that would depart Earth orbit, fly to and land on the moon, take off, and then return directly to Earth. A primary question of the time was to whether to use one large rocket booster of the proposed Nova class, about the size and no doubt the weight of the Empire State Building, or to use a number of smaller rockets to launch parts of the spacecraft into Earth orbit where they would be assembled and fueled prior to departure. In either case, the configuration of the craft to be landed on the surface was unknown, but assumed to be large. In order to obtain experience here on Earth in landing such a large machine on the moon, the initial Flight Research Center idea was to build a craft that would carry the actual lunar landing craft or a replica of it. The carrier craft would include those systems which would compensate for the change in gravity and atmosphere, permitting the spacecraft to simulate free flight lunar descents and landings. It was an impractical idea, considering the fact that no one knew what the spacecraft would look like. In January of 1962, FRC proposed a free flight lunar landing simulator program consisting of three parts: a preliminary study, a research test vehicle, and an Apollo flight simulator. The research test vehicle would be small, relatively inexpensive, and independent of the actual Apollo configuration. It was intended to investigate the inherent problems of lunar descents from altitudes of up to 2,000 feet and have the capacity to vary control characteristics, cockpit configuration, displays, and landing gear geometry, and so on. They considered a helicopter and a lunar vehicle of the same mass over Earth in the helicopter, and if there were no drag, the horizontal component of acceleration would be approximately proportional to the tilt angle of the rotor. Over the moon, where there is definitely no drag, and weight is only 1/6 of Earth, the same amount of acceleration requires nearly 6 times the tilt angle. The proposed technique for simulating the lunar gravity was simple in principle. reduce the apparent weight of the craft to its value while flying over the moon. The proposed method: install a jet engine underneath or within the machine on gimbals, so the thrust was always vertically upward. The engine thrust would then be adjusted so that the craft's net weight, that is, its gross weight minus the engine thrust, would equal its lunar equivalent. Traversing large pitch or roll angles, of course, requires either more time or more control power. It was suspected that the control characteristics that were ideal here on Earth may not be at all acceptable over the moon. The force required to lift the net weight would be provided by throttleable rockets. With the proposed 1-year construction time and a 2-year flight test program, it was believed that the results could significantly assist the design team at North American Aviation, who had just won the contract for the Apollo spacecraft a few months earlier. In the proposed third phase, an Apollo landing simulator would be constructed based on the flight test results from the research vehicle and the developing configuration of the Apollo spacecraft. It would, of course, also be a free-flying machine used to develop procedures and techniques and equipment and, of course, be used for Apollo crew training. The research test vehicle was estimated to cost about $2.5 million, and a full-blown Apollo simulator about 12. At that same time, at NASA's Langley Research Center in Virginia, a small group of engineers, including John Hubel, were devising a new concept: lunar orbit rendezvous. It was a revolutionary idea, using only one big rocket to launch 2 spacecraft modules, one designed for flying from the Earth to lunar orbit and around the moon and then back to Earth, a second lightweight craft designed specifically from descending to the from lunar orbit to landing on the moon, returning to lunar orbit, and then be discarded. Considering that the United States had not even put a man into orbit, the idea of rendezvousing 2 separate manned machines in lunar orbit was thought by many to be ludicrous. But the advantages were tempting. No requirement to launch that monster, build that monster Nova rocket. No requirement to launch a fleet of rockets. No requirement to assemble the lunar machine in Earth orbit. And perhaps most importantly, a potential 2-year saving in reaching the end of the decade goal and about $2 billion in cost. By the summer of '62, the lunar orbit rendezvous technique and its resultant new vehicle, the Lunar Excursion Module, had been approved. In November, Grumman on Long Island was selected to design and build the LEM. Apparently, the word excursion was regarded by some as sounding too much like a holiday and was deleted from the designation. LEM was still pronounced the same way, but its acronym was now just LM. 3 months later, on the other end of New York State, in Buffalo, Bell Aerosystems was awarded a contract to design and build 2 lunar landing research vehicles. As the LEM was not yet designed, there could be no attempt to match its configuration. Once it was decided to use the lunar module specifically for the descent and landing job, the research requirements were much more easily focused. The general configuration converged rapidly, and teams at both NASA and Grumman began laboratory simulations of the control characteristics, touchdown accuracy, visibility, and display requirements. The early simulations were universally done on analog computers. Digital machines of the time were far too slow for flight simulations in real time. The first lunar flying simulations were conducted using helicopters. Unfortunately, they were incapable of investigating the problems of most concern. They could neither replicate the consequences of lunar gravity nor the handling qualities of reaction control systems on those kind of machines. They could approximate a range of final descent trajectories, but that often required flying for substantial periods on the wrong side of the deadman's curve. The X-14 might be a useful simulator, some thought, although it could not duplicate the effects of reduced gravity. Its reaction control system was quite variable and could replicate a wide variety of control characteristics that were directly applicable to lunar flight. Some lunar final approach simulations were performed in early 1964, but without the lunar gravity characteristics, they were of limited usefulness. Independently, at NASA's Langley Research Center, an alternate approach to lunar simulation was initiated. The Lunar Landing Research Facility, LLRF, looked like a dirigible hangar after a tornado. Again, the idea was to duplicate the lunar gravity and control characteristics. The method was to lower the vehicle apparent weight to its lunar equivalent by lifting upward with a vertical cable attached to a traveling bridge crane. A complex electro-hydraulic system kept the crane platform directly over the machine and the cables vertical with an upward force equal to 5/6 of the vehicle weight. It had a wonderful assortment of structural and cable stretch and pendulous frequencies requiring innovative compensation networks. It was indeed an engineer's delight. After the kinks were worked out, it worked reasonably well. The flying volume, 180 feet high, 360 feet long, and 42 feet wide, was limiting, but it was adequate to give pilots a substantive introduction to the lunar flight characteristics. Because the cable system could be frozen at any time, it did permit flying into marginal conditions that would not be attempted in a free flight vehicle. At Buffalo, the LLRV, the Lunar Landing Research Vehicle, was taking shape, but encountering significant cost overruns. NASA FRC was unable to get enough money from the Apollo program, and so it happened that the components were shipped to Edwards, and the NASA team, with some assistance from Bell, assembled the vehicle, installed the systems, and performed the component and systems checkouts. As flight operations neared, they moved the entire operation to Edwards South Base, where there would be a minimum of ground and airborne congestion. The first flight of the LLRV in October of '64 was flown by Joe Walker. First liftoff was what you might call tentative. The second was considerably smoother. On the third, a failure in the control system electronics put the machine in backup mode, creating limit cycling in all axes. The offending relay was replaced, and that failure never reoccurred. On the second flight, a manhole cover lifted and sailed by the LLRV struts, leg struts, as it was flying over. The manhole covers were soon welded down in the flight test area. During the following year, Joe Walker and Don Malik flew about 150 development flights, expanding the flight envelope and investigating the adequacy of the design and the systems. and they had a myriad of flight control configurations that were possible. Early flights had casters on the landing gear, but the wind would push the machine around on the ramp, and the casters had no brakes, so they were later replaced with foot pads. This is usually the part of a flight test program when the unexpected is commonplace. The LLRV was no exception. Modifying or fine-tuning the various systems was a common occurrence. The devil was in the detail. The auto throttle needed to know the vehicle's instantaneous weight, so accuracy of the onboard system to weigh the machine in flight was critical. That turned out to be complicated. EMI was a problem, and devising appropriate electronic filters was an everyday job. The aerodynamic drag compensation was contrary. Uneven feeding from the lift rocket propellant tanks created roll unbalances, which were solved with a unique roll trim system. It took a year to get the kinks rolled out. The flying bedstead could be flown as a conventional VTOL, if there is any such thing, with the jet engine gimbals locked in position and the jet engine providing all the lift. The engine was a vertically configured version of the GE CF700, a J85 core fitted with an aft fan. It had 4,200 pounds of thrust at 87 degrees Fahrenheit, which provided a thrust-to-weight ratio of 1.05. On hot days at Edwards, the thrust-to-weight dropped below 1, and the lift was delayed until some fuel was burned off. But the turbofan performed flawlessly throughout the entire program. In the lunar simulation mode, the engine, mounted in a double gimbal, was aligned to the local vertical and thrust automatically adjusted to reduce the apparent weight of the LLRV to its lunar equivalent. The engine's angle could additionally be modulated to compensate for aerodynamic drag, and the throttle adjusted to counteract vertical drag. When in the lunar simulation mode, lift was provided by a pair of throttleable 500-pound max thrust rockets fixed to the fuselage outside the gimbal ring. The monopropellant was a 90% solution of hydrogen peroxide. In the lunar simulation mode, as you can see, the engine is aligned approximately with the local vertical. Pilots generally preferred flying in the VTOL, or Earth mode, because of the ability to start and stop translation rates with small attitude changes. Decelerating in the lunar simulation mode, conversely, was like trying to stop a downhill putt on a fast green. Uncontrollably large attitudes were required for reasonable decelerations. Altitude control, on the other hand, was very much better in lunar simulation. Response time for the jet engine throttle changes was about 1 second, while the lift rocket's response was only 24 milliseconds, providing very crisp control. The LLRV cockpit was outfitted with a conventional stick and rudder pedals, a standard console throttle for the jet engine, and a collective stick for the lift rockets. The attitude control system was a dual fly-by-wire system. To the best of my knowledge, it was the first fly-by-wire system that did not have a mechanical backup. There was also a dual set of attitude control thrusters, which could be ground adjusted, giving a wide range of control power. Stick and rudder deflection in the primary mode could command angular acceleration, angular rate, or attitude. Obvious to everyone here, having the CG located on the engine centerline was highly desirable. Out of balance conditions could only be compensated by attitude thruster firings. Similarly, as airspeed increased, the drag and the aerodynamic moments would increase, and flight control system would have to work harder and harder to counteract them. That meant the Attitude rockets were firing more and more frequently. Warning lights would indicate to the pilot when roll attitude thrusters were firing excessively, and flight controllers on the ground would radio warnings when telemetry indicated that the thrusters reached 80% of saturation. The pilot would then slow down to reduce aerodynamic moment and could activate both attitude control systems if required. As you all know, if you want cool temperatures and calm winds in the desert, early morning is the time to fly. It was perfect for the LLRV. High thrust and smooth air. The lunar landing research activity was conducted in 1966. Don Malik and Jack Kluver flew about 50 flights, many of which focused on determining the optimum control characteristics of the lunar module. LLRV flights demonstrated that much lower control powers were acceptable than had been expected based on VTOL experience. It was a welcome surprise because low control powers result in low attitude control propellant consumption and weight. Other investigations delve more deeply in how to minimize aerodynamic effects, an evaluation of various final descent trajectories in the lunar simulation mode, and various cockpit and control changes to make it more compatible with the lunar module. Don Malik and Jack Kluver at the 10th SETP Symposium 41 years ago gave a paper on this work. To my knowledge, that was the last SETP paper given on the program and possibly the last in any professional society. In their concluding remarks, they said, quote, "The value of the LLRV for lunar landing simulation seems to be unexcelled," end quote. And that completed the development and research phases of the program. The 204 flights had accumulated 16.8 hours of flight time, an average about 5 minutes per flight. It was time to put the machines to work doing what they were hoped they could do, preparing Apollo crews to make successful lunar landings. The machines were moved to the NASA Manned Spacecraft Center's flight operations at Ellington Air Force Base in Houston. During 1965 and 66, it was increasingly obvious that there was a need for a trainer that was more consistent with the lunar module, whose physical characteristics were now becoming established. Building a lunar module that would fly on Earth like a LLRV was possible, but prohibitively time-consuming and expensive. Serendipitously, the LLRV, although predating the lunar module, was not all that different in physical size and control rocket geometry. An advanced version of the LLRV, modified to match the LEM characteristics, could be built relatively cheaply and quickly. And so the Lunar Landing Training Vehicle, or LLTV, was born. It featured a partially enclosed cockpit with a LEM-like visibility, a 3-axis control-mounted side stick, a lift rocket throttle replacing the collective, LEM displays, a rate command attitude hold system that closely approximated the expected lunar module performance. The LLTV proved to be an excellent simulator and was highly regarded by the Apollo lunar module crews as necessary to lunar landing preparation. But it was unforgiving. 3 of the vehicles were lost, one due to a loss of propellant pressurizing gas, one when wind shear produced aerodynamic rolling moments that the control system couldn't handle, and one due to a primary electric system failure where the switchover to the backup system failed. The Weber ejection seat could operate successfully at 0 altitude with a 30 foot per second downward vertical velocity, the best performance of any seat up to that time. NASA management was forever worried about the reliability and safety of these machines and continually wanted to shut them down. but the pilots insisted they were vital to lunar landing preparation, and they prevailed. The LLTV flight syllabus for Apollo commanders was typically 22 flights, beginning with gimbal-locked hover and transition, then flights with the turbofan aligned to the local vertical, then increasingly difficult final approaches to landing in the full lunar simulation mode, with the control power and rate command attitude hold system matching the lunar module. Typically, the pilot took off with the gimbals locked, flew out to the inner marker, which in this case was about 400 to 500 feet altitude, about a quarter of a mile from the intended touchdown spot. Arriving at the IP, he began a descent toward the target, switched into the lunar simulation mode, energized the lift rockets, and practiced a lunar landing. Often, they would change the desired touchdown point in mid-approach to add more complexity to the task. I was most fortunate to be involved throughout the entire lunar flying development, beginning with the Lunar Research Test Vehicle proposed in 1961. I had the pleasure of flying every one of the machines, the helicopters, the X-14A, the LLRF, the ground-based simulators, the LLRV, the LLTV, the lunar module, and even the Weber ejection seat, the last not by choice. Now the United States is planning to return to the moon. Perhaps, as Jeff Williams reported yesterday, as early as 2018 or shortly thereafter. And when that craft is on final approach to that flat-tipped rock ridge near Shackleton Crater, I hope that the person at the controls has a simulation experience that is at least as good as the LLTV provided the Apollo crews a half-century later. Thank you.